Welcome everyone to 2.2. We're going to be determining volumes by slicing today. I'm still recovering from some surgery last week, so if you're wondering about what's going on up here, that's what's going on up here. All right, so this is really where we start moving into 3 dimensions. We'll be in 3 dimensions for a couple of sections, and it's a little hard to draw things. I'm going to be using images from the book, images from the internet and stuff like that to hopefully help you visualize what's going on, because if we can visualize what's going on, it's going to make the calculus a lot easier. And again, whenever you can in this whole section, kind of this whole chapter, if you can visualize or get a picture or a mental image in your head, it's going to go a lot better. So I want to start by just recalling something that you may or may not know about cylinders. Let's say if I have a cylinder, let's say it's a right cylinder, means it's standing straight basically. And the cylinder has a circular base with radius r and height h. Then we know the volume of the cylinder is just the area at the bottom times the height. In fact, that's not true. That's true for kind of any surface like this. If it wasn't a circular base, if it was a square base, well, it'd just be the area of the bottom, length times width, if it was square, times the height. It could be any shape bottom, and as long as it's the same all the way up, you just multiply by the height and you're good. So what we're doing in this section is what happens if this area is not the same all the way up. So again, like in this, every single cross section, like if oh crap. All right, I accidentally switched pages and then it doesn't let me undo, so we're stuck with this guy forever. But every little cross section, in other words, if I slice horizontally on here like a cake, then that should all be the same circle, no matter where I slice, right? Any cut I make on this, that resulting cross section will still be the same size. To better show what I mean when I'm talking about cross sections, let's use the book, because again, pictures are hard. In this cylinder example, right? If we cut it, mathematically, we're thinking about the intersection between a plane and this solid. In this cylinder situation, we get the exact same shape with the exact same sizes everywhere. Now, what happens if that's different? So we can think about pottery, for example. Maybe we're doing some pottery and we're curious about this shape. Now notice this shape at the bottom has this might be the base actually. I'm not very familiar with pottery. The shape at the bottom is like a little wider, and then it gets a little thinner, and then it gets a little bigger. And in fact, if you kind of trace what's going on here, we got a nice little curve. We could use an equation to model that curve. Right? And basically what's happening here is that every single cross section is going to be kind of like a circle, but they're all going to have different radiuses. So how do we find that volume when it's not the same everywhere? That's what we're doing in this section. So let's look at another pottery example. We're going to come back to this later. But notice that what we have right here, let me try to copy this down a little bit. Copy this little shape. So it starts off a little big, and then it gets a little smaller, and then it kind of gradually grows and bigger. So, you know, we have this sort of thing, and then it gets a little thinner, and then it gets thicker again, and this is mirrored. 3 dimensions are hard. So again, if we look at this pottery thing, that's supposed to be the same shape. So pretend these are the same shape and it's not crooked, right? And that's our base. Well, we could take a cross section anywhere we wanted. And the way that pottery works, it's going to be circular. Now here, it's going to have a small circular radius. Oh, doing an undo is hard when I do a dashed lines. And then up here, right, it's going to be a big circular radius. So let's set up this problem into calculus. What we can do, they all have different radiuses. Let's just look at any single one, any single cross section. And specifically, let's say, well, we want the volume. So if we divide this into a bunch of really thin disks, now let's go into 3 dimensions. Really thin disk, we can find the volume of this disk. This is just a little cylinder, a tiny little cylinder. What's the volume of this red shape? Well, it's a cylinder. Volume of the red shape is going to be its area, which is pi times the radius squared. Well, what's our radius here? Well, the radius is going to be different at any height. And in fact, the radius, if you think about this guy over here as a curve, or this blue guy over here as a curve, and this as the y-axis, then in this case, the radius is just the function value in terms of y, because it's sideways. So what we really have right here is that the volume of this tiny little thing is going to be pi times the radius, which again is going to be the function value. And here it's a function value of y because, again, we're looking at a vertical graph instead of a horizontal graph. You could do it both ways. And that's getting squared. That's the area of that little guy. And what's the area, what's the height of this tiny little cylinder? It's some really tiny thing that we can call dy or delta y. And so if we add up all of these, right, this is just one little tiny red cross section, little chunk, little tiny cylinder. If we add up all of those and make them thinner and thinner and thinner, we get a good approximation of the volume, and that's calculus. So that's the overview of this section. Now, I don't expect anyone to just go, oh, yes, I understand everything. This makes perfect sense right now. But that's a high-level overview of what's going on here. This is how integrals are going to be connected, because we're dividing things into tiny pieces, adding them all up. That'll give us some integrals. So let's do an example and then introduce a more formal way of doing these problems. And as the section goes on, we'll get more and more formalized, more and more information, more and more connections. But this is basically what's happening here. All right, so example 1. We know the volume of a pyramid is 1/3 the area of the bottom times height. Let's see. Show this is true for a equals 2, h equals 3, using something I'm going to call slicing. I haven't introduced slicing yet, but I want to show it to you before I give the, the formal thought process. I want to show you what exactly we're doing. Again, this is just an introductory video. So I want to introduce it. Okay, so here's what's going on. We're always going to want pictures. So there's 2 ways that we can draw this pyramid. One's maybe a little easier than the other for some people, but it doesn't really matter. We have a pyramid. It has a square base. All right, and we know that the height of this pyramid, it's kind of hard to show. The height of this pyramid is 3 units, and the base is 2 by 2. So we know the volume. We can find the volume just this way. But let's try to find the volume using cross sections and integrals and show that it should match up. So again, we know the volume should be, right, 1/3. The base is 2 times the height is 3. 3's cancel. It should be 4 units cubed. That should be the answer. Let's think about these with integrals. Again, I haven't formally introduced the method, just introducing what's going on. So for all of these problems, we're going to look at little cross sections. So imagine we're cutting out a little piece of this pyramid. So this piece is a square, right? If we do a horizontal cut at any level in a pyramid, we have a square. And the question is, at any height h, what are the dimensions of this square? Well, it's a square, so this dimension should be the same as that dimension. We need to find its dimensions. So that's usually the hard part here. How can we find the dimensions of any cross-sectional square of this pyramid? So this is where a picture is going to be very, very important. Couple ways of doing this. You can look at the bottom of the square, the bottom square, the base. You look at the top. You could try to rotate this and write it as a function. But I think the easiest way to do this is to just look at where we're starting at height 0, what's happening, and at the top, what's happening, and then what's the relationship along the way. So at the base, at height 0, it's going to be 2 by 2. Right? At height 0, when h is equal to 0, when we're at the very bottom, this is a 2 by 2. So the side length of this yellow guy is going to be 2. When we're at the very, very top, what's the side length? Well, when we're at the very, very top, when we're at 3, the cross section has gotten so small, there is no side length, right? It's just a single point. There is no square at the top. Then what's the relationship along the way? It's a linear relationship, right? Notice that this is a straight line. So as we're gradually going up, it's a very constant side reduction. So similarly, right, you can add more of these, right? If we're halfway up, what's the side length going to be? It's going to be 1. And so on. We essentially have similar triangles here. Another way of approaching this, because this is kind of heuristic, it's not really formal. Another way of seeing this, and this is, again, the struggle for this entire section, is going to be visualizing these things. Again, let's look at our pyramid. Whoa. I don't know why this pyramid looks so weird. This pyramid looks really bad. I don't like this. Makes me uncomfortable. It looks like really slanted. So another way of visualizing this, does this help? I don't think that helps, but whatever. Another way of visualizing this is looking at triangles. Think of a triangle going up the side of this pyramid, where this wall is going up the right side of the pyramid. Again, really hard to visualize and draw these things. Well, we have a relationship here. At the bottom, it's side length 1 of this triangle, because just half of 2. The top is still 3. Well, then what's the relationship at any other height? Well, at any other height, it's a similar triangle. You can set up similar triangles here to get the relationship that way as well. You'll get a slightly different setup, but you'll get the same answer. 2 ways of finding this. So again, this is a linear relationship. What's the slope? And again, there's a couple of ways of doing this. depending on the height. We want to find the slope so we can find the linear relationship between h and a. Okay. So again, let's have h be our independent variable and a be our dependent variable. There's a ton of ways of setting this up. Find a way that works for you. Now, what we know about slope is it's going to be difference in y. So let's just pick 2 points. Those 2 points are probably the easiest. Or you can actually look at this. It's going to be the change in y. So in this case, the change in a, we'll choose this point as our second and this point as our first. So the change in a is 0 minus 2 divided by 3 minus 0. Or in other words, negative 2/3. So what's the relationship? Well, let's use point slope form. Y minus one of the a's, again, let's just choose that first point. Or sorry, not y, a minus one of those a's, let's choose that first one, is equal to the slope times our independent variable minus that same. Again, if we're looking at this first point using point slope form, and that'll give us our relationship between a and h. So a is just 2 minus 2/3 h. Now this is a little backwards from what we wanted. So it probably would have been better if I switched these. But it doesn't matter. It works either way. So we're saying at any height, what is that cross-sectional area? So, oh no, we did do it right. Yeah, we did do it right. At any height, a is 2 minus 2/3 h. And we can just check this. This is what we think. This is going to be useful. Well, let's just kind of check it in our heads. At h equals 0, when we're at the bottom, when h is 0, our side length should be 2. When we're at the bottom, our side length is 2. That's good. Oh. Yeah, and when we're at the middle, when h is 3/2, what's our side length? 2/3 of 3/2 is 1. So when we're at the middle, the side length is 1, just like we thought. Good. And similar at the top, when h is 3, our side length is going to be 0. So we found that the cross section looks like this. At any height from the base, this is what our cross section looks like. Well, now if we just add up those infinitely tiny areas, adding up an infinite number of infinitely tiny things, that's integrals. That's calculus. We should get the volume. We're going to get the volume is just the integral. Well, we're starting at an h value of 0. We're going up to an h value of 2. And at any cross section, what's the area? It's a square. Just a times a. 2 minus 2/3 h squared with respect to h. And we can evaluate this integral and we'll hopefully get 4. Remember, we already know the answer should be, we already know the answer should be 4 units cubed. So let's evaluate this real quickly. You can either do a u substitution here or FOIL it out. Your choice. I think foiling it out is a little bit more straightforward. I think a u substitution would be a little quicker. We FOIL it out. What we're going to get is 4 minus, I'm using a u substitution. It's easier. You can FOIL it out if you want. Let u be 2 minus 2/3 h. Then du dh equals negative 2/3. So we need a negative 2/3 here, which means we need a negative 3/2 out here. And then look what happens. Negative 2/3. Du is negative 2/3 times dh. So this is our du right here. And this is just u squared. Now we don't have to FOIL it out at all. All that's left is where do our limits go? If x is 0, u oh, sorry, not if x. If h is 0, what's u? U is 2. If h is 2, what's u? Oh, wait, h is not going from 0 to 2. H is going from 0 to 3. Remember, our height is 3. If h is 3, what are we at? We're at 0. This now is just going from 3 to 0 instead of 0 to 3, and u squared. So I know this is a lot. That's okay. We'll do a lot more practice in the next video, just kind of introducing some methods, and then we'll formalize it at the end of this video. So we get negative 3 halves. Antiderivative is u cubed over 3. We want to evaluate that from 3 to 0. Well, this is kind of nice because the 3's cancel. We just have negative a half times u cubed is 0 cubed minus 3 cubed. Uh-oh. Small issue here. H equals 0 is a u value of 2. I was just thinking everything was 3's. But when h is 0, you can see that the u is indeed just 2. So all of these should just be replaced by 2's over here. And then again, we get 2 cubed, which is 8. And 8 halves is indeed 4 units cubed. All right, and that's just another way of showing the volume of a pyramid. So let's formalize this and finish this introductory video and get you the tools for us to maybe more clearly work this stuff out. All right. So here's the slicing method. I'll introduce it and show that we were actually doing it. First is draw a picture including cross sections. At least one cross section. So that's step 1. We did that step 1 right here. We drew our picture. We had our cross section right here. Excellent. Step 2 is find the area, this was really the hard part, of the cross section. And there's no single way of doing this step 2. We did it over here. Now, it's going to be different every time. You're going to have to use what you know about geometry, what you know about lines, what you know about circles. It's really not calculus based at all. And this way that I did it is the way that made sense to me. It's not the easiest way. It's just my natural way. Find your way that you can figure these out. Everyone's going to be problem solving differently. And that's what can be a hard part of this section, is you just kind of have to use your tools in a way that works for you. And there's not going to be a single way that always works. But the important thing is you find this cross section, the area of this cross section at any height, however you're going to do it. As a side note, if you had this pyramid upside down, it actually is a lot easier to solve. But I wouldn't expect anyone to know that, so I'm showing how I would have gone about it if I didn't know the easy way. I can't just always show the easiest ways, because most of the time, we're not going to be doing the easy ways. Most of the time we set these up however we see them, and that's okay. That's good. All right? You don't always have to find the perfect solution to start. And then step 3 is going to be integrate the area to get volume, which again is exactly what we were doing in chapter 1. Remember in chapter 1, we said, hey, how do I find this area? We divided it into little tiny approximate pieces and said, okay, what happens if this width gets really small? That's integration. Adding up an infinite number of infinitely tiny things. And that's exactly what we're doing over here. We said, let's look at a single tiny little chunk. Just a tiny slice. What does the volume look like? We found the volume here. It was the volume of a circle, of a cylinder. And we added up, again, if we were doing it this way, we'd add up an infinite number of infinitely tiny things this way. I don't know, we use C and D. If it's in terms of Y, we'll formalize this process too. Here, we added up an infinite number of areas at any height. And well, we're starting at a height of 0 on this pyramid, and we're going all the way up to a height of 3 on that pyramid. That's what we're integrating over, or the height. So again, this is tough. We're going to do more examples. We're going to do more problems, but this is the slicing method, and this is how we can find volumes. Let me know if you have any questions, and good luck.